Okay, thank you everyone for coming. I see there is a big attendance to our workshop, so we feel already successful for it. Thanks to Jasmine, who planted the seed to start what now is the workshop. Jasmine and I started discussing this, then we opened it up to Ramon, and then now we have like a little plant of quantum cognition in Chile. So we are now watering the plant with this workshop. So my talk will be mainly about introducing to everyone who is not acquainted with the theory, with the basic foundations. So this is a very general talk. I will talk about quantum cognition concept, about the concept itself and how we interpret what it means, because it sounds really sexy, quantum cognition, for this 21st century, but we really need to understand what it means. So that's the funny first part. Then I will talk a little bit about the history of our sense. I mean, the people who do research in this workshop, what kind of our, because we are not really a team, but we more or less share the same understanding. And then developments and expectations, which will be mostly explained by the other speakers. And I will end up with some like reflections and perspectives of the field. So when we say quantum cognition, I put the plus in between. It's like a game for transforming meaning into mathematical formulas. So what do we mean by plus when we say quantum and cognition? So an interesting approach to understand the meaning of two words together, it's to check the meaning of the words in isolation. So we will expect that the meaning of the two words together will be maybe related or can be constructed from the meaning of the words in isolation. So there is a lot about this thing coming in today. So we will talk a lot about what is to put things together and what comes out and whether those things are related or not to the constituent and to the understanding of the constituents when they are in isolation. So quantum, it's a word for amount, and in the modern understanding, it's the basis of quantum theory. And the idea of quantum is that things are quantized, so they have a basic unit. I will explain a little bit of this later. And cognition is the ability to acquire, process knowledge and understanding. It's a very open, big word. So it's all about thinking and experiencing, sensing, etc. So I will dig a little bit more into the theory of cognition and the theory of quantum. So quantum theory, it's basically a mathematical description of the weird behavior of microscopic entities. So it's a very quick definition. And when I say weird, I mean some particular things that have been observed and are strange to our first understanding of reality, physical reality. So the first and the reason why quantum theory is called quantum is because physical properties are discontinuous. So fundamental physical quantities cannot possess any value, but only specific values. And that goes against the previous understanding, the Newtonian understanding of the world, where things can have, like, where any physical measurement can have any possible value and not just particular values. So I will show a little video to explain this that comes from that website. And we have a French speaker who can translate for us, but I will mention. So this is the idea of the spin, which is one interesting quantum feature. Like, it's a physical property actually that is related to magnetism. So in classical theory, we have that if we send certain magnets through this to this dipole, we will see that depending on the magnetization on the magnetization of the elements we send, we will observe how they respond to the field, to the magnetic field. So, and their response can have all sorts of possible values, all possible values. Whereas in quantum particles, they have spin which responds in a definite way, which is only positive, let's say, or negative. And there are no values in between. So spin is a quantum property in the sense that you will only observe it like spin up, or you will observe it spin down. You will not ever observe a spin magnetic response like neutral response as you will observe with classical magnets. So I go very fast just to show it's really nice to check those videos. You will see other properties, and the other interesting feature is the contextual existence. So fundamental features of objects depend on how they are measured. So the universe of objects, the view of the universe as a collection of objects, is an illusion because the objects are not there. They will be created, or they will acquire their structure by the process of observation. And that's something really deep. It's hard to compress this in 1 second, but I would like you to check this video. I will remain silent because it's really clear. That explains the nature, the weird nature of quantum objects. Classical particles. Classical waves. The response will show a interference pattern. Quantum objects behave both as particle and wave. That's the strange thing. But if you have the observer, then it will behave again as a particle. So this is about to end. Okay, so that was the idea to explain, and I know we cannot like dig deeper into this, and there will be, the other speakers will also explain some aspects of quantum theory, but the idea is that it questions the fundamental understanding of reality that we have and proposes some new structure. So in cognitive theory, when we remember, we have quantum, cognition, and now I'm explain a little bit of quantum, now a little bit about cognition. So cognitive theory is a formal description of the cognitive phenomena, and the cognitive phenomena is something really, really big as what quantum theory wants to explain, which is the physical realm. The cognitive realm, it's another less understood, I will say, aspect of our reality, and it involves the brain as the architecture where thoughts occur. It involves as well another important concept, the mind, which is the realm of thought, which we don't know where it is, if it is somewhere in the universe, or if we need some metaphysics to explain it properly. We don't even know that. We have language also, which is the manifestation of thought, like written language expressions. Learning, another important concept, the capacity to modify thinking towards a goal, but that's our current understanding, I mean, literature understanding. Consciousness, the capacity to think about thinking, or maybe some other definitions. These are just like bold, quick definitions. And the interesting thing is that different aspects of cognitive theories focus on different realities, and they have different theoretical bases, and they work with different types of data. So that's the interesting or a good summary. So we have mind, brain, and information approaches to cognition. So the theoretical basis can be psychology, neuroscience, or artificial intelligence, and the data will be human perception and behavior in this case, or brain signals, or some like more basic signals of the body, or corpus of text or images, like massive information. So depending on which approach to cognitive theory, to cognition we have, we will work with different types of data, and probably with different assumptions, which will build up different theories. So there is a lot of literature about this, a lot of stuff. And actually, the current understanding of how to study cognition is at least merging all these fields, AI, anthropology, linguistics, philosophy, and this is known as cognitive science. So cognitive science is like the umbrella where all cognitive theories are receiving shade from. And it's a very big field, very fuzzy. It has many aspects, because the very understanding of cognition is so complex. So now remember, we're trying to explain what quantum cognition is. Like this is my main goal of this talk, to explain you what quantum cognition is and what is not, a little bit. So we can attribute at least two possible meanings to quantum cognition. One will be brain phenomena relies on quantum processes. Then cognition is a quantum phenomenon. And we will then think of all the fundamental physical processes occurring in the brain at the microscopic level, and how that influences the functioning of the brain. And then that will be a basis to understand how cognition emerges from quantum phenomenon. That's one approach. But another approach is to think that the mind phenomenon is quantum-like. So we are not talking about the brain, but about the mind. So cognition is a quantum phenomenon. So this is the side on which we will focus on, not on thinking about the brain, mostly not. But in order to understand now what quantum cognition is in this interpretation, we will have to explain what mind phenomena is and what quantum-like means. So this approach then is not so much about the brain, about the physical architecture where thoughts occur, but more about the very structure that they deliver when we measure them. So behavior or decision-making behavior, or data in general, like information data. So this approach, the approach that we will talk about today, is much more aligned to the idea of psychology rather than neuroscience, and artificial intelligence as well. So I will try to go quick. So mind phenomena, what is the mind phenomena? We have perception, and we have data for perception. So these are, when we observe this, I can ask you which colors you see, which forms you see, or what is your perception about sound, etc. Or in decision making, we can measure that. We can make experiments, or we can take opinion polls, or voting, political elections, and so on. All that is behavioral data. Of course, not to mention marketing and all that, like Facebook or Cambridge Analytica and so on, all that data, which relates to these corpuses of data. Thinking of the internet as a global mind, full of collections of texts and images and multimedia data. And then the web or Google, like companies, process this data and provide a structured data. So define categories, which is a little bit like behavior, human behavior, but at a global scale. So that's the sort of mind phenomenon that we want to tackle and we want to explain. So we will exclude neuroscience data, again, as I said, because it's the behavior of the architecture, not the behavior of the mind, not the mind phenomenon. So this is just maybe I'm not sure if someone will speak more about that today, but like the explanation I'm telling is excluding this. And by quantum-like, which is the funny thing of quantum cognition, is that quantum theory is a probabilistic theory, and there are statistical footprints that reveal quantum structure. And quantum structure is what I said before, weird structure that you will not be able to explain by taking a classical standpoint. And by classical, I mean classical probabilistic, which is where most cognitive theories are developed. So the idea is that when we have statistical footprints of quantum structure, then we can make quantum models. And quantum models means use the mathematical apparatus of quantum theory to make a model of a cognitive situation. But not just cognitive, it can also be different. It can be another thing, not necessarily cognitive. So back to the double slit experiment, for example, we have a physical reality and we have a mathematical model of physical reality, which is the quantum theory or the classical theory. And then we have statistical data and we have probabilistic predictions of our mathematical modeling. So if we change this physical reality by mind reality, by psychological data, for example, then it's the same picture. That's the point I want to stress. I will stress later with some examples. So the major quantum structures, the major footprints, statistical footprints, is to when we see things that seem to be and not be at the same time, which I will explain like in a minute, we speak about superposition in quantum terms. When we see that crucial features of things seem to depend on the observation process, on the process when we consider them part of the reality, then some crucial features seem to emerge, then we speak of contextuality. And when collections of things behave radically different from the aggregated behavior of individual things, then we speak about non-compositionality, and these properties are somehow footprints of quantum structure. When these things occur, we know that probably a quantum model will perform better than a classical model. So now I will show examples of these cases. For example, in perception, there is a study about this classical picture that you can see either two faces or a glass or a cup. So how can we model the understanding of a bistable? It's called bistable perception. So how do we model this? So the perception of some images cannot be reduced to a single interpretations. Multiple interpretations can coexist, and the mind shift from one, revealing the statistic, and that shifting can reveal the statistical structure of the quantum process. So the bistable perception and the way we shift our mind from one interpretation to another has been shown to be better explained as the superposition of images rather than a probability to interpret the image on one way or another in a classical sense, as a stochastic process, for example. So, and this, for those that know a little bit of linear algebra, will be to think of the interpretation of the image as a superposition of two orthogonal vectors, one meaning the interpretation that the image reflects faces, and the other interpretation reflected that the image is the image of a glass. That's one footprint, and this has been observed in many other cases. I cannot explain in longer. I just want to give the glimpse of bistable interpretation in our mind can be a superposition of interpretations, so a superposition of understandings. There are also categorization experiments where where people are asked to categorize objects for different categories, and some categories are singular and other are composite. So for example, olive, I ask you, is it a fruit, a vegetable, or fruit or vegetable? So fruit or vegetable is a composite category, and we want to see what is the structure of that composite category in our minds. Can we directly deduce it from like a classical understanding from our understanding of vegetable and fruit. So then we can mark this preference. So how much do we believe that olive is a fruit, or vegetable in this scale? And then it turns out, when you see this categorization data, that the way people statistically believe that an object is part of a concept is very much similar to the way in which data of the double slit experiment is created. So we have to interpret this part of the picture as passing through slit A, this part of the picture as passing through a slit B. So in between is where you don't know if it passes through slit 1 or slit 2, slit A or slit B, sorry. So then when we create this fruit or vegetable data, membership data, we tend to see interference pattern instead of a logical pattern, which will be, well, B is more aligned or A is more aligned. So there seem to be, as it can be explained in this sentence, fruits or vegetables is not a mental state formed by the logical combination of the concepts fruit and vegetables, which will show like the classical pattern of more preference towards fruit or more preference towards vegetables and nothing in between. But a mental state where concepts are superposed. So this is, in categorization, we can see that people tend to create statistical data that reveals interference patterns between concepts. So I will show this little model that instead of thinking now on the physical case, we think that this is an object, a mind emitting objects that will be categorized. So this double slit is a categorization, fruit, vegetable. And then we see the interference pattern will be how much preference towards fruit or towards vegetable you find. And in the middle case, which is the most likely to happen, it reflects the uncertainty state. So, and that's sort of like the footprint of the statistical structure we were mentioning. So again, back, we have the mathematical model, and we see that for concept fruits, we can model the data as a single wave, as you can see, like a wave that is, like in the first example in the video, you can see the wave for fruit and a wave for vegetable. And this is actually a model that can tell you the preference, a statistical preference of people, like if they will be waves. And then for the composite concept, the fruit or vegetable, you will see that the data matches the interference pattern of these two waves. So the interference pattern of these two waves is not trivial because it's not a classical wave, it's a complex wave. So there are complex numbers involved, and that's why you will see so many weird, the interference pattern will be so weird and not just like something simpler. And that is, in a glimpse, an explanation of how categorization can show statistical footprints of quantum theory. Now, to speak about contextuality, I will give you a very quick example again about these three questions. Are you in favor of nuclear energy? Do you think it will be possible to legalize soft drugs? And do you think it is better for people to live in a capitalistic system? With these three questions, we will assume, the classical modeling will assume that the probability function for these three questions exists. So it tells you the probability that you say yes, yes, no, 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 yes, any combination. So that's something that normal cognitive theories will assume. But the problem is that when you make this assumption that there is a universal view of the three answers together, and that we can make a classical model, we have that the probability function has to also fulfill certain mathematical conditions that is called marginal probabilities. and some other laws of probability will have to be fulfilled. So the interesting thing is that this will always happen if people will have a definite answer prior question. But when people do not have a definite answer prior the question being asked, it is possible to find contradictory configurations in the preference when you look at the statistical answers. So these contradictory answers that you find, statistically contradictory answers, are the footprint of the quantum structure I'm mentioning. It's a little hard to explain in so short time, but there are the statistical structures I'm mentioning. There are mainly inequalities. When the data leaves certain region, you know that this cannot come from a classical theory. So the interesting issue of this is having a relatively small proportion of undetermined preferences, you can obtain the contextual footprint. So I will show with this, which is like 15% of people with 70% of undetermined answer. If 70% of undetermined answer is in your set of people for the question you will ask, it is easy to show, and this is part of an article that I will share now, that these are completely likely probabilities. These are probabilities you can have. So probability for Q1, given that Q2 is yes, probability for Q1 yes, given Q2 is yes, 0.78 and so on. So you can obtain a certain probabilistic data, show that it's a feasible example of data when people have no definite answer. And also it is possible to prove a contradiction from this data. And that's the trick. You can prove that simultaneously, no, yes, yes must be larger than 0.28 and smaller than 0.11. This is a mathematical proof. But the interesting thing, or what I want to keep clear, is that there is a way to show that there is no universal view on the probability, on the probabilities you observe. They come from a contextual process. So opinions can be contextual as well. And this is observed when you do priming, on when you work on order effects, on when you see contradictory behavior in general, and a large, etc. in cognitive data. So there are contextual phenomena in cognition, which can be represented by the quantum structures, or at least you can show that there are no classical. And that's the paper which you can look at in case you are interested. So, and to end, I will discuss the non-compositionality phenomenon, which is like when you combine concepts, there is the meaning of the combination can reveal a statistical footprint that is called entanglement. And the entanglement is found, or it's represented when the statistics of the measurements to the single entities differ radically from the statistics of the compound entities. And this is mathematically well defined. It's again a statistical inequality, which I will not explain because it will become too technical, but you can see in a simple example. If you have the word apple, you can think at least more generally in these two meanings. If you have the word chip, you can think of these two meanings, two different meanings, the chip and the food chip. And then if you put together the apple chip, then there is one interpretation that is a chip devised by Apple, which is basically a combination of these two interpretations, and the other interpretation, which is the combination of the apple and the food chip. So the two interpretations become meaningful. And most people will respond to them directly. And there are other interpretations that will be kind of forbidden. They will never, or occur very little in people's mind, which is the other interpretation, this mixing this with that, which is chips on your Apple computer, for example, or this other, which is introducing a chip or like 5G kind of I forgot the word, like people who believe things like really, really strange things, like apples can have chips. So this other interpretation might also become forbidden in our minds. It's not forbidden in the sense that we are not allowed to think of it, but we will just simply never come up with this quickly. So there are two interpretations that become more salient, and this saliency is what it reveals this new structure, because the probabilities here and here for the two interpretations might be very 50-50 or pretty much 50-50, but then the way in which these other two become more salient is the statistical footprint that I was mentioning. So I hope this introduction is useful for you. So explaining that there is a quantum theory, there is cognitive phenomenon that does not fit classical explanations. So you have to look for quantum mathematics, let's say, to tackle this phenomenon. So the coming talks of the workshop will explain much better, in much more detail, the applications of quantum-like modeling, either in paradoxes problems interpreting color, sound, and vision perception, or about fuzzy and non-compositional categorization, or irrational decision-making. So these are pretty much the topics that will be covered today in the talks. And it's very, and meaning modeling, which is probably not today, but it's another line that is very interesting and developed today. So to finish, I want to mention, like, in the perspective of why discussing quantum cognition, why thinking about this. So the question raises from the very bottom, saying what are the fundamental entities of meaning and how these entities are structured and interact. We already know, and we could almost certainly say that these entities do not behave as if they would be classical objects, not even objects. So the nature of meaning is not objectual. So we tend, when we use classical probabilistic theories, it is a little hard to tell in a nutshell. But when you do probabilistic theories, you start from the assumption that things are objects and that the probability of observing something will be related to the proportion or to the amount, let's say, or to the size of this object. And all these notions that things have size, things are contained in groups, these are collections of things, these are all classical notions. So meaning is something much more strange than our current understanding of an object. So that's why you need to change kind of like the epistemology or the fundamental concepts, but the fundamental concepts by which you build up understanding of what meaning is. That's the deep question. And the point is that the mathematical apparatus of quantum theory and also the concepts that are used to explain the ontology of quantum entities has shown that or show that the meaning entities don't have the structure we are accustomed to think of. So this ideal notion that an apple as a concept is somewhere structured, we should kind of start forgetting about it. It's something much more complex, because the entities exhibit these structures that I was mentioning, which are like the footprints of quantum theory, and sharply defined boundaries. The shape is co-created with the act of thought. So meaning is not somewhere. I mean, that's what can be found from data. And also meaning is non-compositional. So if we understand that the very basic stuff that we study in cognitive science hold some properties that imply that its structure cannot be represented properly by classical thinking, then we must leave the classical thinking for cognitive theories And quantum cognition is a proposal to use instead the apparatus of quantum theory for explaining cognition, cognitive data, cognitive phenomena, not the brain, but just to remind. So even many researchers now think that we should go further than this. Than is twice in the presentation is a correction, automatical correction from the Spanish. So perhaps we should go further than quantum and simply think of non-classical structures. So also many researchers say that quantum cognition is not a good name because it should be just non-classical probabilistic cognition and not quantum, because quantum also is attributed to physical reality. But the field is also plenty of discussions about how, many hows. So to end, for the perspectives, there are many things coming now. So for example, the language modeling and artificial intelligence, incorporating all these ideas of contextuality and vagueness and non-compositionality to Siri-like applications, for example. This is something kind of strange, but it is very likely that future models of language will incorporate these structures. Generative expectations and creativity. It's another important field because in the quantum structures allow you to have a kind of broader perspective on what is to combine things, and then that's why it is related to creativity and the contextuality and empathy, which is something that I like very much to think of, is that understanding that reality is contextual makes nobody right. Nobody is ultimately right, because we all have our own context, our own understanding, and thus empathy is something that comes like kind of natural. There is no other way to understand better reality than being empathetic, because no one holds the ultimate truth, right? So if this is proven, no one holds the ultimate truth, then empathy is a sort of the smartest move instead of being like close to your own thinking. So contextuality is something that can drive to empathy. And also on a philosophical note, just to finish, it is also interesting to explore the very nature of reality, more than physics and more than cognition. So what is reality at the very end? So now we just proposed today that concepts and all the cognitive meaning phenomena is like quantum particles, behaves like quantum particles. But the other way around would be, what if quantum particles are really like concepts? Can we shift the very nature of reality and think that reality, instead of being physical, is conceptual? So this is what it is called, the conceptuality interpretation. And with this, I really finish now. Sorry for too long.
Thomas,
yeah.
Sorry for interrupt you, but we are almost done with your presentation.
Yeah, this is my last slide. So with this, I finish. Sorry, Ramon. So if human entities are associated with quantum-like behavior, then one can introduce that the microphysical entities should be associated with conceptual-like behavior. That's the idea. So this conceptual substance forming our global reality might be even independent of us humans. So there can be a fundamental, this is kind of philosophical and weird, but there can be a fundamental conceptual nature of reality that is beyond us and beyond our understanding of physics. So understanding the nature of concepts, the nature of meaning, might be the key to understand the physical reality. And that's with the thing I want to finish, thanking the organizers, the speakers, and you for attending. Thanks.